This is precisely the sort of puzzle that awakens astronomers from their beds. A prediction that confident, failing that completely for that long does not mean the prediction is wrong. It means the tools are wrong. The search for black holes in Omega Centauri failed for decades because every detection method available required the black hole to announce itself, to emit radiation, to pull in gas, to do something visible. These black holes were doing none of that. They were simply sitting in the dark, exerting gravity on whatever happened to drift close enough. One star drifted close enough, curved its path, and Hubble recorded the whole thing over 20 years without anyone realizing what they had until recently. One found, 9,999 still missing. And the method they used to find it is going to change how we look at every dense cluster of stars in the sky. On a clear night from the southern hemisphere, you can find Omega Centauri with your naked eye. It sits in the constellation Centaurus, a smudged point of light that looks at first glance like a slightly out of focus star. From a truly dark sight, no city glow, no moon, it resolves into something more unsettling. It spreads, it grows. On the best nights, from the best locations, Omega Centauri spans nearly as much sky as the full moon. Not a point, a patch. A dense, faintly glowing disk hanging above the southern horizon, ancient light that has been crossing space for 17,700 years just to reach your eyes. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Point a small telescope at it, and the effect is immediate. The smudge sharpens into a swarm. Thousands of individual stars emerge from the glow, packed tighter toward the center, thinning out toward the edges, the whole thing organized into a rough sphere of light. The center is almost too bright to resolve clearly. Stars so close together that from Earth, even a decent telescope starts to blur them back into a haze. From space, the Hubble images show something different. Millions of individual points, a city of stars so dense that in the core region, the average distance between neighboring stars is less than 1/10 of a light year. Our nearest stellar neighbor, Proxima Centauri, is 4.2 light years away. Inside the heart of Omega Centauri, stars that close would be considered almost lonely by comparison. The numbers take effort to absorb. Omega Centauri contains roughly 10 million stars, all of them gravitationally bound together, orbiting their collective center of mass like a single object. The whole structure spans about 150 light-years from edge to edge. For reference, the distance from our Sun to its nearest neighbor is 4.2 light-years. Pack enough stars together that the average gap between them shrinks to a fraction of that. Then repeat that compression across 150 light-years of space, and you begin to approach what Omega Centauri actually is. Its total mass adds up to roughly 4 million times the mass of our Sun. Not 4 million stars at solar mass, 4 million solar masses total, including all the stars, all the remnants, all the dark objects that have accumulated inside it over billions of years. That mass figure matters because it puts Omega Centauri in a category almost by itself. A typical globular cluster, and the Milky Way contains over 150 of them, holds somewhere between 100,000 and a few 100,000 stars. Modest objects by the standards of this galaxy, Omega Centauri is not a modest object. It is roughly 10 times more massive than the next largest globular clusters in the Milky Way. The gap between Omega Centauri and its nearest competitors is not a small step up. It is a completely different weight class. Astronomers sometimes describe it as almost as massive as a small galaxy, and that comparison is not an exaggeration made for effect. There are actual galaxies orbiting the Milky Way with fewer stars and less total mass than Omega Centauri carries inside its 150 light-year diameter. To feel what that density means, try a different kind of comparison. If you shrunk the entire distance from our Sun to the edge of the solar system, out past Neptune, out to the boundary where the sun's influence starts to fade, down to the size of a marble. Then Omega Centauri at the same scale would be a sphere roughly the size of a small house. Inside that house, 10 million marbles, every marble a star, most of them packed within the inner rooms. That is the environment inside Omega Centauri's core, an almost incomprehensible density of stellar objects, orbiting each other, passing each other, occasionally colliding, constantly interacting through gravity, over timescales that dwarf anything in human experience. The cluster is old, very old. Its stars formed mostly more than 12 billion years ago, in the earliest chapters of the universe's history, when the first generation of large-scale structures was condensing out of hydrogen gas. The universe itself is about 13.8 billion years old. Omega Centauri has been gravitationally bound and orbiting for most of that time. The stars inside it have lived and died and left their remnants behind across billions of years of continuous stellar evolution. Some of those remnants are white dwarfs, the cooling cores of sun-like stars. Some are neutron stars, the hyperdense corpses of stars that ended in moderately powerful supernova explosions. And some of them, the ones this whole story is ultimately about, should be black holes. Should be. That word is doing a lot of work. Because here is the thing about a place this massive, this dense, this ancient. The physics of stellar evolution is well understood enough to make confident predictions. Massive stars, those above roughly 8 times the mass of our Sun, burn fast, live short lives by stellar standards, and end in explosions violent enough to leave black holes behind. Omega Centauri has been running that process for over 12 billion years, across 10 million stars, many of them from an era when star formation preferentially produced larger, heavier objects. The math of how many of those stars lived and died and collapsed into black holes is not speculative. It is grounded in well-tested models of stellar evolution applied to a cluster whose properties astronomers have measured carefully. The answer the models produce is somewhere around 10,000 black holes, not a handful, not hundreds. 10,000 still inside the cluster, still orbiting, still gravitationally embedded in the same structure they formed inside. A place that crowded, that massive, that ancient, should be absolutely full of black holes. And for most of the last century, astronomers could not find a single one. Omega Centauri has been stared at for almost 2,000 years, which is longer than most cities have existed. The first person to write it down was Claudius Ptolemy, the Greek-Egyptian mathematician and astronomer who catalogued the visible sky around 150 AD. In his Great Star Catalogue, Ptolemy listed what we now call Omega Centauri as a single star. That was not a mistake. That was the limit of what human eyes could resolve at the time. From the ground, without any instrument at all, the cluster looks like a slightly fuzzy point of light, not unlike a dim star sitting just above the plane of the southern sky. Ptolemy saw something real. He just could not see what it actually was. That stayed the official understanding for roughly 15 centuries. The object sat in catalogues, copied and recopied across generations of astronomers, labelled as a star, filed away and largely forgotten in the way that dim and apparently unremarkable objects get forgotten. Then Edmund Halley looked at it. Halley, who is remembered mostly for the comet that carries his name, was also one of the most systematic observers of the southern sky in the 17th century. In 1677, working from the island of St. Helena in the South Atlantic, he turned his instruments toward this particular point in Centaurus and noticed something that Ptolemy's unaided eye had missed. It was not sharp. It had no clear edge. It did not resolve into a crisp point the way a true star does, even under magnification. Halley classified it as a nebula, a word that at the time meant simply a cloudy or diffuse object of uncertain nature. He was closer to the truth than Ptolemy. He still was not there. The step from nebula to globular cluster came in the 1830s, and the person who made it was John Herschel. Herschel, son of William Herschel, who had discovered Uranus and spent decades cataloguing the northern sky, took the family project south. He set up at the Cape of Good Hope in what is now South Africa and spent 4 years systematically mapping the southern heavens. When he turned his telescope toward the fuzzy object in Centaurus, he could actually resolve what it was. Individual stars appeared, not a cloud of gas, not a featureless glow, but discrete points of light packed so tightly together that earlier instruments had blurred them into a single smear. Herschel identified it correctly as a globular cluster, a gravitationally bound sphere of stars, and wrote up his observations with the careful precision that characterized everything his family touched. It was a fundamental reclassification. The object that Ptolemy had called a star, that Halley had called a nebula, was now understood to be an enormous congregation of stars held together by mutual gravity. What is striking about this three-stage progression is how it maps directly onto the quality of the instruments available at each moment. Ptolemy had eyes. Halley had a modest telescope that could separate the object from the background, but not resolve the stars within it. Herschel had a larger and better calibrated instrument, set up under dark southern skies, and the individual stars finally separated from the blur. Each observer was doing the best they could with what they had. Each one arrived at a conclusion that was reasonable given their data, and each one turned out to be wrong in a way they had no way of knowing at the time. This pattern did not end with Herschel. Astronomers in the late 19th and early 20th centuries studied Omega Centauri intensively, measuring its stars, mapping its brightness distribution, estimating its distance. Each generation believed it had a solid picture of the object. Each generation was working at the edge of what was technically possible, and each generation left the next generation something unexpected to find. The distance estimates kept being revised, the star count kept going up, the total mass of the cluster kept coming in larger than anyone had assumed. This is not a story of past scientists being careless or naive. It is a story about what happens when an object is genuinely more complex than the tools available to study it. The revision happening right now is different in character from the previous ones, but it follows the same basic structure. Ptolemy did not know it was a cluster. Halley did not know the nebula was made of stars. Herschel did not know the cluster might be the stripped core of an entire galaxy. And every generation since has been missing the same thing. A dark and invisible population of objects scattered through the interior, present the entire time and completely undetectable by every method anyone had tried. Every time a new generation of astronomers turned better instruments toward it, the object they thought they understood turned out to be something more complicated than the generation before had realized. To understand why Omega Centauri is so strange, you have to start with a question that most people never think to ask about a star cluster. Where did all these stars come from? For most globular clusters, that question has a clean answer. They formed early, all at once. In the first few billion years after the Big Bang, enormous clouds of primordial gas collapsed under their own gravity, igniting hundreds of thousands of stars in a single furious burst. Then the gas was gone. The burst was over. What remained was a gravitationally bound family of stars that had all been born in the same place, at the same time, from the same raw material. Every star in a typical globular cluster carries that shared history in its chemistry. They are old. They are metal poor, meaning they formed before the universe had produced many heavy elements. And they are essentially uniform. Point a spectrometer at one star, then at another on the opposite side of the cluster. The chemical signatures look nearly identical. Same age, same composition, same origin story. Omega Centauri does not work that way. When astronomers began measuring the chemical compositions of stars across Omega Centauri in detail, what they found was not uniformity, it was chaos. Stars spread across a wide range of metallicities, some carrying almost no heavy elements at all, consistent with forming very early in the universe. Others containing significantly more, consistent with forming later, after previous generations of stars had already lived, exploded as supernovae, seeded the surrounding gas with heavier material, These are not subtle differences. The range of metallicities inside Omega Centauri spans a factor of roughly 50. No simple globular cluster does that. A factor of 50 in chemical enrichment requires time. It requires multiple generations of star formation. It requires a system complex enough to hold onto gas, recycle it through dead stars, form new stars from the enriched remains. That kind of extended history takes something more than a globular cluster. It takes something closer to a galaxy. Here is the picture astronomers have built from those chemical clues. Billions of years ago, long before the Milky Way looked anything like it does today, a small dwarf galaxy drifted into our galaxy's gravitational reach. It was not a massive galaxy, nothing like the Milky Way itself, but it was its own system, with its own stars spanning multiple generations, its own chemical history, its own dense gravitational core. As it fell deeper into the Milky Way's gravity well, the forces acting on it became unequal. The side of the dwarf galaxy closer to the Milky Way felt a stronger pull than the far side. That difference in gravitational force, called tidal force, began stretching the dwarf galaxy apart. The outer stars, held more loosely by the dwarf galaxy's own gravity, were the first to go. They were pulled away, scattered into long streams that wrapped around the Milky Way like ribbons. Star by star, the outer layers of that ancient dwarf galaxy were peeled off and absorbed into our own. What was left was the core, the densest, most tightly bound part of the original galaxy, the region where gravity held on hardest and longest. That surviving core is what we now call Omega Centauri. This is not fringe speculation. The stripped galaxy hypothesis is the leading explanation among researchers who study Omega Centauri in detail. The evidence for it accumulates from multiple directions. Beyond the chemical diversity of the stars, there is the cluster's sheer mass. At roughly 4 million solar masses total, it is about 10 times heavier than the next most massive globular clusters in the Milky Way. If you want to explain why a globular cluster has 10 times more mass than other globular clusters, an obvious candidate is that it was never really a globular cluster at all. There is also the presence of what appears to be a massive black hole at the cluster's center, the kind of central concentration of mass more consistent with the nucleus of a former galaxy than with a simple cluster of stars. The implications of this origin story go well beyond astronomy's interest in ancient galactic mergers. They reach directly into the question of what happened to all the massive stars that lived and died inside Omega Centauri over billions of years. A simple globular cluster forms in one burst, burns through its most massive stars quickly, then settles into a long, quiet existence populated mostly by lower mass stars that age slowly. The massive stars that could have produced black holes are mostly gone in the first 100 million years or so. A former galaxy is a different story. It had multiple generations of star formation, each one producing new massive stars, each wave of those stars eventually dying and potentially leaving black holes behind. The chemical enrichment that astronomers measure in Omega Centauri stars is itself the record of that repeated cycle, massive stars forming, burning fast, exploding as supernovae, enriching the gas, triggering the next generation. Each cycle could have added to the population of compact remnants left inside the core. Black holes from the first generation, black holes from the second, black holes from generations that formed under chemical conditions very different from anything in a typical cluster. If Omega Centauri was once a full galaxy, its interior has been a factory for black holes across a much longer and more complicated history than any normal globular cluster could claim. If the leading hypothesis is correct, Omega Centauri is not a globular cluster at all. It is the fossil core of a galaxy that our Milky Way swallowed whole. It has been hiding inside our own backyard for billions of years. Every star that has ever lived inside Omega Centauri has left something behind. Not light, not memory, something physical, a corpse, the remnant of a nuclear furnace that burned for millions or billions of years and then went dark. When our sun eventually dies, it will leave behind a small, dense ember called a white dwarf, about the size of Earth, slowly cooling over trillions of years. That is the fate of ordinary stars, stars with modest masses. But Omega Centauri has not been filled with modest stars, and the stars that die violently do not leave embers. They leave something far stranger. To understand what Omega Centauri is hiding, you have to understand what happens to a star when it has too much mass. The threshold is roughly 8 times the mass of our Sun. Below that line, stars age gracefully. They swell, they shed their outer layers, they leave behind a white dwarf. Above that line, everything changes. A star with 8 or more solar masses burns through its hydrogen fuel with a kind of reckless speed. Where our Sun fuses hydrogen for roughly 10 billion years, a star 20 times as massive might exhaust its core fuel in as little as 8 million years. That sounds long from a human perspective. On astronomical timescales, it is nothing. These stars live fast and end catastrophically. When a massive star runs out of hydrogen in its core, it does not simply fade. It starts burning helium, then carbon, then oxygen, then silicon. Each stage of fusion produces less energy and runs out faster until the core is mostly iron. Iron is the end of the line. Fusing iron absorbs energy rather than releasing it, and the core collapses almost instantly, in less than a second, under its own gravity. The outer layers of the star, suddenly unsupported, come crashing inward and then rebound outward in a shockwave of almost incomprehensible violence. The explosion, a core collapse supernova, can briefly outshine an entire galaxy. If this fascinates you, consider what it means inside Omega Centauri, where millions of such events have been playing out for over 12 billion years. What the explosion leaves behind depends on how much mass the core had when it collapsed. For stars on the lower end of the massive range, the core compression produces a neutron star, an object roughly the size of a city, packing more mass than our Sun into a sphere about 20 kilometers across. Neutron stars are extreme objects, but they are not black holes. For stars heavier than roughly 20 to 30 solar masses, or in some cases even less depending on the details of the collapse, the core mass exceeds the limit that even nuclear forces can support. Gravity wins completely. The core does not stop collapsing. It collapses without limit into a region of space where the escape velocity exceeds the speed of light. Nothing comes out. That is a black hole. So every sufficiently massive star that has ever died inside Omega Centauri has left behind a black hole. The cluster has been forming stars for over 12 billion years. Many of those early stars were massive. The universe itself was younger, the gas clouds richer in primordial material, and the conditions in a dense protocluster environment were favorable for producing heavy stars in large numbers. Each one that formed, burned, and exploded contributed a black hole to the cluster's population. That process did not happen once. It happened over and over across billions of years, across millions of stellar generations. Here is where the numbers become striking. Astronomers use something called an initial mass function to describe how stars of different masses are distributed when a population forms. Heavy stars are rarer than light ones, but they are not vanishingly rare. In a cluster as massive as Omega Centauri, with a total mass equivalent to roughly 4 million suns, the initial mass function predicts that a substantial fraction of all stars ever formed cross the threshold for leaving a black hole remnant. When researchers apply standard models of stellar evolution to a cluster of this age and this mass, the answer that keeps coming out is approximately 10,000 stellar mass black holes. 10,000. Not 10, not 100. 10,000 individual black holes, each one the collapsed remnant of a star that burned and exploded inside this cluster at some point in its 12 billion year history. And here is what makes that number permanent. Black holes do not decay. They do not drift away into the surrounding galaxy on any short time scale. They are massive enough that the cluster's gravity holds them. The typical velocity needed to escape Omega Centauri is higher than what most objects inside it carry. A stellar mass black hole, once formed inside the cluster, is essentially trapped. It circulates. It sinks toward the center over time through a process of gravitational friction with surrounding stars. It interacts. It does not leave. The cluster is old enough, and these objects are dark enough, that every black hole ever formed inside Omega Centauri is almost certainly still there. The arithmetic of stellar death is straightforward, and when you apply it to a cluster as old and massive as Omega Centauri, you end up with a prediction. Somewhere inside that cluster, roughly 10,000 black holes are sitting in the dark, waiting to be found. The prediction of 10,000 black holes inside Omega Centauri was not a guess. It came out of decades of careful theoretical work, built on established stellar physics and refined computer simulations of how dense clusters evolve over billions of years. Astronomers weren't estimating. They were calculating. They fed known quantities into well-tested models. The cluster's age, its total mass, its initial population of massive stars, and the standard rules of stellar evolution. And the models returned the same answer repeatedly. Roughly 10,000 stellar mass black holes should be sitting inside Omega Centauri right now. The number was not controversial. It was almost mundane in how consistently it appeared. What was controversial was the fact that nobody could find them. To understand why the prediction was so confident, you have to understand what happens to black holes once they form inside a cluster. A black hole produced by a collapsing massive star doesn't stay where that star died. It moves. Clusters are not static. The stars inside them are constantly exchanging energy through gravitational interactions, passing close to each other, nudging each other's orbits, slowly redistributing mass throughout the system. This process has a direction. Heavy objects sink, light objects float, in the same way that sediment settles to the bottom of a lake while lighter material stays suspended near the surface. Black holes, which are significantly heavier than the average star, gradually drift toward the center of the cluster over millions of years. Astronomers call this mass segregation. It is not a dramatic process. It takes a long time, but over billions of years it is relentless. By the time Omega Centauri had reached its current age of roughly 12 billion years, the models said most of its black holes should have migrated toward the central regions, piling up in the core where the density is already extraordinary. They should have been packed together, interacting constantly, dynamically pairing up with each other or with nearby stars. The core of Omega Centauri, by these calculations, should have been crawling with them. The models also made specific predictions about the masses of those black holes. And this is where Omega Centauri's particular chemistry became important. Not all stellar environments are the same. Stars are not made of pure hydrogen and helium. They contain trace amounts of heavier elements: carbon, oxygen, iron, silicon, and astronomers group all of these together under the single label of metals. A star's metallicity is simply its abundance of these heavier elements relative to hydrogen. This matters enormously for how a massive star lives and dies. Metal-rich stars, those with higher abundances of heavy elements, drive powerful stellar winds during their lifetimes. These winds peel away the outer layers of the star before it ever reaches the end of its life. By the time the star finally collapses, its core has been whittled down by all that mass loss. The resulting black hole is lighter than it would otherwise have been. Metal-poor stars work differently. With fewer heavy elements driving those winds, the star holds onto its outer layers. Less mass escapes during the star's life. When collapse finally comes, the core is heavier. The resulting black hole carries more mass. Omega Centauri is a metal-poor environment. Its stars formed in conditions where heavy elements were scarce. In the early universe, before successive generations of supernovae had seeded the galaxy with the metals that later stellar populations would inherit. This means that the massive stars which lived and died in Omega Centauri over its long history retained more of their mass before collapsing. The theoretical prediction wasn't just 10,000 black holes. It was 10,000 black holes that were likely heavier than the average stellar mass black hole found elsewhere in the galaxy. Some models suggested many of them would fall in the range of 20 to 50 solar masses or more, depending on the specifics of the progenitor star. Omega Centauri was theoretically an ideal factory for producing a massive and numerous population of black holes, and it had been running that factory for 12 billion years. This is the kind of prediction that gets astronomers out of bed. It was specific, it was physical, and it was testable. You had a precise number, a predicted mass range, a predicted location inside the cluster, and a clear mechanism explaining all of it. Every piece of the theoretical picture fit together cleanly. The mass segregation argument explained why they should be concentrated toward the center. The metallicity argument explained why they should be on the heavier end of the stellar mass range. The stellar evolution argument explained why there should be so many of them. Nothing in the theory was hand-waving. It was grounded in the same physics that successfully described black holes and stellar remnants everywhere else in the universe. The prediction had survived scrutiny for years, before the search for the objects themselves began in earnest. And then the searches came back empty. Repeated studies, different instruments, different methods, different teams approaching the problem from different angles, each one expecting to confirm what the theory had laid out so clearly, and each one coming back with nothing definitive. The cluster that the models described as full of black holes appeared, observationally, to be hiding every single one of them. The gap between what the theory said should be there and what the observations could actually find grew wider with each passing decade, and nobody could agree on which side of that gap contained the error. The models were solid, the physics was agreed upon, and the number kept coming out the same. And still, for decade after decade, the black holes stayed hidden. For decades, the search for black holes in Omega Centauri looked like a search for something that did not exist. The prediction was not ambiguous. Models of stellar evolution, applied carefully to a cluster as old and as massive as Omega Centauri, kept producing the same number, roughly 10,000 stellar mass black holes. Not a rough estimate, not a speculation, a mathematically grounded output of well-tested physics, agreed upon across research groups, consistent across decades of refinement. The cluster was old enough. It was massive enough. The stars that had lived and died inside it were numerous enough. Everything pointed to a swarm of dark remnants sitting somewhere in that dense ball of ancient light. And yet, every time astronomers turned their instruments toward Omega Centauri looking for black holes, they came back empty-handed. The first serious searches used X-ray telescopes. This is the standard opening move in black hole detection. When a black hole pulls gas off a nearby companion star, that gas accelerates and heats to temperatures of millions of degrees before it crosses the event horizon. At those temperatures, it radiates in X-rays, bright and unmistakable. X-ray observatories like Chandra have found black holes this way in binary systems throughout the galaxy, in other globular clusters, in the centers of nearby galaxies. The method works. Astronomers pointed Chandra at Omega Centauri and looked carefully at every point of X-ray light inside the cluster. A handful of sources turned up. None of them matched the signature of a stellar mass black hole, actively pulling in material from a companion. The cluster, that was supposed to hold 10,000 of these objects, showed nothing credible at all. Then came the radio searches. Jets launched near accreting black holes produce radio emission, and that emission can be detected at enormous distances. Radio telescopes scanned Omega Centauri repeatedly. The searches were sensitive. The searches were thorough. They found nothing. No coherent radio source inside the cluster that could be attributed to a black hole feeding on a companion star. Zero detections, zero candidates. This is the kind of result that makes you check your instruments. Both methods had returned the same verdict, and the verdict made no sense given what stellar evolution was predicting. So astronomers tried a third approach: radial velocity measurements. The idea here is straightforward. If a visible star is in orbit around an invisible massive companion, the star will be periodically pulled toward us and then away from us as it traces its orbit. That motion shows up in the star's light as a slight shift in wavelength, a Doppler shift that repeats on the orbital period. By measuring these velocity shifts for thousands of stars in Omega Centauri, researchers hoped to catch stars that were being tugged rhythmically by something dark and massive. The technique had worked beautifully elsewhere. It had found exoplanets, it had found neutron stars, it had found stellar mass black holes in other environments. In Omega Centauri, it produced nothing reliable. The cluster is extraordinarily dense, and at a distance of nearly 18,000 light-years, individual stars are packed together on the sky in a way that makes clean spectral measurements extremely difficult. The light from neighbouring stars bleeds together. The velocity signals the method depends on get buried under noise from overlapping spectra. A few intriguing candidates emerged from various studies, but none survived close scrutiny. What looked like a possible gravitational tug from a dark companion kept dissolving under better data into something more mundane: a crowded field, an unresolved background star, a statistical artifact of measuring too many faint objects too close together. By the late 2000s and through the 2010s, the field was in a genuinely uncomfortable position. 3 independent detection methods, 3 independent sets of null results, and a theoretical prediction that refused to go away. When a confident prediction fails this persistently, scientists typically consider 2 explanations. The first is that the prediction is wrong. Maybe the models of stellar evolution in metal-poor environments are missing something. Maybe Omega Centauri's history was different enough from what the models assumed, that the black hole population is much smaller than expected. Or maybe the black holes were somehow ejected from the cluster over billions of years through gravitational dynamics. Some researchers pushed this line of thinking seriously. Papers were written exploring whether dynamical processes might have depleted the black hole population more aggressively than models suggested. The second explanation is that the prediction is right and the detection methods are failing, not because the instruments are bad, but because the methods have a built-in requirement that the black holes have to be doing something visible. X-rays require active accretion. Radio emission requires jets. Radial velocities require individual stars to be cleanly resolved from their neighbours. If the black holes in Omega Centauri are mostly isolated, mostly quiet, and mostly embedded in one of the most crowded stellar environments in the galaxy, all 3 methods could fail simultaneously while the black holes sit there perfectly real and perfectly invisible. Over time, the second explanation gained ground. The absence of X-ray and radio detections was itself informative. Most black holes, most of the time, are not actively accreting material. A black hole sitting in empty space, not feeding, not paired with a close companion, produces no signal that any of these methods could detect. The black holes might simply be dark. The frustration in the field was not drama. It was a genuine scientific impasse, a mismatch between what the universe was predicted to contain and what the tools at hand were capable of seeing. The models said 10,000 black holes should be in there, and the instruments kept returning the same answer: nothing, or at least nothing that could be confirmed. The tools that had found black holes everywhere else in the universe simply did not work inside Omega Centauri. That is not a small admission. These were not obscure or untested methods. X-ray astronomy had been finding black holes since the 1970s. Radio telescopes had traced jets from accreting compact objects across thousands of light-years. Radial velocity surveys had unmasked invisible companions around stars in dozens of other clusters. The toolkit was proven, and astronomers had every reason to trust it. The problem was not the tools themselves. The problem was that Omega Centauri is a fundamentally different kind of environment, one that breaks the assumptions baked into every conventional detection strategy. Start with X-ray and radio methods because they dominated the search for most of the last half-century. When a black hole pulls gas off a nearby companion star, that gas does not fall in quietly. It spirals inward through a structure called an accretion disk, heating up as it compresses, reaching temperatures of millions of degrees by the time it nears the event horizon. At those temperatures, the gas stops glowing in visible light and starts screaming in X-rays. In some systems, magnetic fields near the black hole launch narrow jets of material at nearly the speed of light, and those jets radiate in radio wavelengths. Both signatures are bright, distinctive, and detectable across enormous distances. This is how astronomers found stellar mass black holes throughout the Milky Way. Pointer, telescope at the right location, catch the glow of infalling matter, measure the signal. It works beautifully when the black hole is eating. Most black holes in Omega Centauri are not eating. They are sitting in the dark, isolated, with no companion close enough to donate material, no accretion disk building up, no jets launching. A black hole that is not accreting produces essentially no radiation at all. The X-ray sky above Omega Centauri looks almost clean, not because there are no black holes, but because the black holes have nothing to announce themselves with. Researchers pointed some of the most sensitive X-ray observatories ever built at the cluster and found a handful of faint sources, most of them explainable by other phenomena entirely. The predicted population of thousands simply did not appear, because thousands of quiet black holes leave no X-ray footprint whatsoever. Radio surveys came up similarly empty. If the black holes are not actively feeding, the radio sky stays silent. The radial velocity method seemed more promising because it does not require the black hole to be active. It requires only a visible star orbiting the black hole close enough and fast enough that the motion is detectable. The technique works by measuring the Doppler shift of the star's light. As the star moves toward us in its orbit, its light is compressed slightly toward the blue end of the spectrum. As it swings away, the light stretches toward the red. By tracking the shifting back and forth over time, you can measure the star's orbital velocity and calculate the mass of whatever it is orbiting. It is the same principle used to find planets around distant stars, and it has worked on objects far more difficult than a star cluster 17,700 light-years away, except that Omega Centauri is not a typical target. The cluster packs 10 million stars into a volume roughly 150 light-years across. From Earth, that translates into a region on the sky where stars are crammed so tightly together that separating their individual light becomes extraordinarily difficult. A spectrograph pointed at any single star in the inner regions of the cluster is almost inevitably catching a blend of light from multiple nearby stars at the same time. The spectrum you measure is not clean. It is a composite of overlapping signals from stars at slightly different velocities, at slightly different distances, moving in slightly different directions. Trying to extract the precise radial velocity of one specific star from that mixture is like trying to hear a single instrument, T, in a stadium full of musicians all playing at once. The technical term astronomers use is crowding, and in Omega Centauri, the crowding is severe enough to make radial velocity work deeply unreliable in the regions where most of the black holes are expected to be concentrated. Distance makes it worse. At 17,700 light-years, individual stars in the cluster are faint. Faint stars produce weak spectra. Weak spectra introduce measurement uncertainties. Those uncertainties grow large enough to swamp the very signal you are hunting. A binary system with a wide orbit, meaning a star moving relatively slowly around a distant black hole, might produce a velocity shift of just a few hundred meters per second. In a crowded cluster at this distance, the noise in the measurement can easily exceed that signal by a wide margin. You would never see it. Searches were conducted, data was collected, velocities were measured for thousands of stars, and the results were ambiguous at best. Nothing that held up under scrutiny. What makes this genuinely frustrating, and what took astronomers a long time to fully reckon with, is that the very property responsible for the failure was the same property that made the cluster so scientifically compelling. The extraordinary density of Omega Centauri is what produces the dynamical interactions that form black hole binaries. It is what concentrates the population of dead stellar remnants in the first place. It is what makes the cluster worth searching. And that same density, that same crushing concentration of 10 million stars was blinding every instrument pointed at it. The crowding that built the black holes was burying them from view. Every method that had successfully found black holes in other contexts broke down in exactly the conditions that should have produced the most of them. When most people hear the phrase black hole, they picture something that devours everything around it, a cosmic drain pulling in light and matter from every direction. That image comes from science fiction, from the swirling accretion disks and screaming jets of material that make black holes look like the universe's most aggressive consumers. The reality is considerably quieter and considerably stranger. There are actually several classes of black hole, and they are not all the same thing. The ones that dominate headlines are supermassive black holes, objects containing millions or even billions of times the mass of our Sun, sitting at the centers of galaxies and occasionally pulling in enough gas to light up as quasars visible halfway across the observable universe. The one at the center of our own Milky Way, called Sagittarius A star, contains roughly 4 million solar masses and sits about 26,000 light-years from Earth. These are the celebrity objects of black hole astronomy. They are genuinely enormous, genuinely active in many cases, and genuinely hard to miss when they are feeding. But they are not the kind of black hole hidden inside Omega Centauri. Stellar mass black holes are a different category entirely. They are the ordinary workhorses of the black hole world, typically ranging from about 5 solar masses up to around 100 solar masses, though some may reach higher. They form when a massive star, one with roughly 20 or more times the mass of our Sun, reaches the end of its life and explodes as a supernova. After the outer layers are blasted away, the core collapses inward. If that collapsing core is heavy enough, nothing stops it. Gravity wins completely. The core shrinks past the point where even neutrons can resist, and a black hole forms. It contains a few tens of solar masses. It occupies a region of space roughly the size of a city. And then, unless something falls into it, it does essentially nothing. This is the part that surprises people. An isolated stellar mass black hole sitting alone in the dark between stars is one of the most invisible objects in the universe. It emits no light, it produces no radio signal, it sends out no radiation of any kind that a telescope could detect. If you were somehow able to fly a spacecraft to within a few thousand kilometers of one without knowing it was there, you might detect a faint gravitational tug before you got into serious trouble. From any practical astronomical distance, you would see absolutely nothing. It is not a drain pulling everything in. It is just a small, extraordinarily dense knot of gravity sitting in the dark, waiting. This invisibility is not a failure of instruments. It is a fundamental property of these objects. Black holes radiate only when material is actively falling into them. And even then, the radiation comes from that infalling material, heated to extreme temperatures as it spirals inward, not from the black hole itself. Stellar mass black holes that are not part of a close binary system, not pulling gas off a companion, not embedded in a dense cloud of gas and dust, produce no detectable emission at any wavelength. X-ray telescopes cannot see them. Radio dishes cannot hear them. Optical telescopes find nothing at the location where they sit. They are, by any conventional measure, perfectly dark. The analogy that makes this concrete is simple. Imagine a dark ocean at night. No moon, no starlight, no phosphorescence. Now imagine a large, smooth, black boulder sitting somewhere on the surface of that ocean. You cannot see it directly. Your eyes find nothing. But if you watch the surface of the water carefully enough, over a long enough period, you will notice something. The waves bend slightly around the boulder. The currents shift in a way that does not quite match the open water nearby. Objects floating on the surface follow paths that curve, almost imperceptibly, as they pass near it. The rock announces itself through what it does to everything around it, not through anything it does on its own. Stellar mass black holes work the same way. This is why Omega Centauri's hidden population proved so resistant to detection for so long. The methods astronomers relied on, X-ray signatures, radio emission, the Doppler shifts of radial velocity measurements, all require the black hole to be doing something. They require it to be feeding, flaring, or actively tugging a nearby companion close enough to measure the back and forth wobble in its light. A quiet black hole in a wide orbit, sharing its neighborhood with a companion star it barely disturbs, produces none of those signals. It is simply present, massive, invisible, and patient. The only reliable way to find a quiet black hole, one not actively eating anything, is to watch what happens to the objects that move near it. The method that finally worked had nothing to do with looking at the black hole directly. No radiation, no heat signature, no signal of any kind from the black hole itself. The technique that cracked open Omega Centauri's hidden population is one of the oldest ideas in astronomy, applied with a level of precision that would have been unimaginable a generation ago. It is called astrometry, and at its core, it is almost embarrassingly simple. You watch where a star is, you watch where it goes, you notice if something is pulling it off course. Astrometry is the science of measuring the precise positions of stars on the sky over time. Not roughly where a star is, not approximately, precisely, down to fractions of a pixel on a space telescope's detector. Fractions of an arcsecond in angular terms, which is a fraction of a degree. When you achieve that level of precision and you hold it across years or decades of repeated measurements, the positions of stars stop being static points and start being paths. You can see movement, you can see curvature, and curvature tells you something is there that you cannot see directly. A star moving in a straight line through space is a star moving under no unusual gravitational influence. A star tracing a curve is a star being pulled. If the thing pulling it is invisible, the curve is the only evidence you have that anything is there at all, and it turns out to be enough. Think of it like this. Imagine you're watching a person walk along a sidewalk, and somewhere around a corner, out of your line of sight, they have a large dog on a leash. You cannot see the dog, but the person is not walking straight. They keep drifting, leaning, changing speed, getting tugged. From the behavior of the walker alone, you can infer that something massive and insistent is on the other end of that leash. You cannot see it. You do not need to. The walker's path through space tells you everything. This is precisely what astrometry does with stars. The star is the walker, the black hole is the dog, the leash is gravity. The physics underneath this is Kepler's laws, the same mathematics that describes how planets orbit the sun. If a star is in orbit around an invisible massive companion, the star's speed at any point in its orbit depends on two things: how far it currently is from the companion and how massive that companion is. When the star is at its closest approach, it moves fastest. When it is farthest away, it moves slowest. This is not an approximation, it is a precise mathematical relationship. So if you can measure how fast a star is moving at various points in its orbit, and if you know roughly how long its orbit takes to complete one full cycle, you can calculate the mass of whatever it is orbiting. The number that comes out of that calculation does not care whether the companion is a black hole, a neutron star, or something else. The mass is the mass. Whatever its nature, gravity does not lie about how heavy something is. This is the critical advantage astrometry holds over every other method that astronomers tried inside Omega Centauri. X-ray detection requires the black hole to be actively pulling in gas and heating it until it glows. Radio detection requires jets of accelerating material. Radial velocity measurements require the star to be moving toward and away from us in a way that shifts the wavelength of its light measurably. All of these methods need something to be happening near the black hole. Material falling in, energy being released, some form of emission crossing the void between the cluster and our telescopes. If the black hole is sitting quietly in the dark, orbited at wide distance by a single companion star, with no gas stream between them. All of those methods go blind. There is nothing to detect. Astrometry does not care. The black hole does not have to do anything. It just has to be massive. And massive things pull on whatever is near them, always, without interruption, without requiring any particular conditions. Gravity is patient in a way that radiation is not. The challenge is that the movements involved are extraordinarily small. A star 17,700 light-years away, tracing an arc across the sky over the course of decades, shifts its position by an amount measured in milli-arcseconds. A milli-arcsecond is 1,000th of 1 arcsecond. 1 arcsecond is 1/3600th of a degree. These are not numbers that inspire confidence in any measurement made from the ground, where the atmosphere blurs and shimmers and distorts everything. To do astrometry at this level of precision, you need a space telescope. You need stability, clarity, and time. You need Hubble. What the research team did was sift through more than 20 years of archival Hubble observations of Omega Centauri, measuring the positions of individual stars frame by frame, year by year, looking for anything that moved in a way the cluster's general drift could not explain. The crowded field made this extraordinarily difficult. 10 million stars packed into 150 light-years means neighbors everywhere, light overlapping light, images blending at the edges. Separating individual stars and tracking the same one across observations taken years apart required painstaking work. Then James Webb came in to sharpen the most recent measurements, its infrared sensitivity cutting through the crowding with finer resolution than Hubble alone could manage. The combination gave the team something no previous search had possessed: long baseline, high precision, and a detection method that did not depend on the black hole announcing itself. The technique required no signal from the black hole itself, no radiation, no radio wave, no X-ray, just the motion of a star that could not move that way unless something invisible and enormously massive was pulling on it. The discovery did not come from a single observation or a lucky detection on one specific night. It came from 20 years of patient accumulation, from a telescope launched when the internet was still a novelty, from archival data that sat waiting in servers for someone to ask the right question of it. Hubble went up in 1990. The observations of Omega Centauri that proved useful for this kind of precision astrometry begin around 2002. That is when the data quality, the detector capabilities, the calibration techniques aligned well enough to make sub-pixel position measurements reliable. From 2002 to 2023, the team had a baseline stretching more than 2 decades. That span of time is the foundation everything else rests on. The raw challenge is worth sitting with for a moment. Omega Centauri contains 10 million stars packed into a volume roughly 150 light-years across. When Hubble images the cluster's central regions, the field is not sparse and clean, it is overwhelming. Stars crowd against each other. Their point spread functions, the smeared halos of light that any telescope produces around a stellar image, overlap and blend. Pulling individual stars out of that field and measuring their positions to a fraction of a pixel requires painstaking work. The team had to identify the same stars across images taken years or even decades apart. Accounting for the fact that every star in the cluster has moved slightly over that time, the cluster itself has its own bulk motion through space. Hubble's detectors are not perfectly stable from year to year. Each of those factors introduces errors. Controlling them is what separates a measurement that means something from one that does not. The process of correcting for all this motion is itself a significant technical undertaking. The cluster moves as a unit across the sky, so the team had to model and subtract that bulk drift to isolate the smaller individual motions of specific stars. Then they corrected for proper motion, the slow drift of each star through the cluster caused by its own velocity relative to its neighbours. What remained after those corrections was the residual signal, the part of each star's motion that could not be explained by the cluster's bulk flow or the star's own trajectory. For most of the 10 million stars in Omega Centauri, that residual is essentially zero, or too small to be meaningful. For a handful of stars orbiting an invisible massive companion, the residual traces a curve. That curve is the signature of a binary system. Finding it means processing the positions of enormous numbers of stars, image by image, year by year, looking for the rare cases where something does not move straight. Not every star in the cluster is a plausible candidate for a black hole binary. The team was specifically looking for stars whose motion curved in a way consistent with an orbital path around a dark companion. Even filtering the full catalogue down to candidate systems involves managing a very large amount of data. Omega Centauri's density is, in this sense, both the reason the search matters and the reason it is so technically demanding. The same crowding that theoretically produces thousands of black holes is the crowding that makes finding any one of them an enormous computational effort. Now, here is why the length of the baseline is not merely helpful, but decisive. The binary system at the center of this discovery has an orbital period of 94 years. The companion star takes nearly a century to complete a single loop around the black hole. 20 years of data captures less than a quarter of that full orbit. That sounds like a serious limitation. In one specific way, it is actually an advantage. The portion of the orbit that falls within that 20-year window happens to coincide with the star's closest approach to the black hole. In any elliptical orbit, the orbiting object moves fastest when it is nearest to what it is orbiting. That is basic orbital mechanics, the same physics that makes comets streak across the inner solar system before slowing again in the cold outer reaches. At closest approach, the companion star's velocity is at its peak. Its curvature on the sky is sharpest. The gravitational fingerprint of the black hole is strongest. 20 years of data, by coincidence of timing, caught the most informative stretch of the orbit. This is the kind of luck that rewards patience. If the observations had begun a few decades earlier or later, they might have captured the slower, flatter portions of the orbit, where the star barely seems to curve at all and the signal nearly vanishes into the noise. The timing was fortunate, and the team made use of every bit of it. James Webb entered the picture at the end of the observation window. Its infrared sensitivity and sharper angular resolution allowed the team to refine the most recent position measurements, adding precision to the data points that were closest in time to the analysis. In the dense stellar field of Omega Centauri, infrared imaging helps separate stars that blend together in optical light, improving the accuracy of each position fix. Webb did not replace the Hubble archive. It sharpened the final chapter of it. Without the Hubble archive stretching back more than 2 decades, the orbital motion of the companion star would have been too slow, too subtle, too buried in the noise to detect at all. Inside the impossibly crowded field of Omega Centauri, one ordinary star was moving the wrong way. To understand what that means, you have to picture what the researchers were actually working with. The field of view inside Omega Centauri is not like looking at a sparse patch of open sky. It is a wall of stars, tens of thousands of them packed into every frame Hubble recorded, each one shifting slowly across the sky as the cluster moves, as individual stars drift within the cluster, as the whole enormous system traces its path through the Milky Way. Most stars in that field, when you subtract out the cluster's overall motion, travel in straight lines. They move with the crowd. They go where the crowd is going. That is normal. That is what you expect. And then there was this one. The star itself is not remarkable. By every standard measure, it is a thoroughly ordinary main sequence star, the kind of object that fills the galaxy by the hundreds of billions. Its mass comes in at roughly 78% of our Sun's mass. It is dimmer than the Sun, slightly cooler, smaller in radius. If you placed it in our neighborhood of the galaxy and looked at it through a backyard telescope, you would not pause on it. Nothing about its light, its color, or its brightness announces anything unusual. It is exactly the kind of star that gets lost in a crowd. Inside Omega Centauri, it was lost in a crowd. That was precisely why finding it took 20 years of observations, measured to a fraction of a pixel. But when researchers laid those measurements across time and tracked exactly where this star was in 2002, where it was in 2010, where it was in 2015, in 2019, in 2023, the picture that emerged was not a straight line. The path curved, not dramatically, not in a way visible to the eye in a single image, but across 2 decades of data. The curvature was unmistakable. The star was being pulled. Something was bending its trajectory through space, with a gravitational grip far too strong to come from any visible neighbour. The arc the team recovered was not a complete orbit, it was far from it. The orbital period of this system turns out to be 94 years, and 20 years of data captures less than a quarter of one full loop. What the researchers had was a fragment of a curve, not a circle, but it was the right fragment. The star, during those 20 years of observations, was passing through the closest point in its orbit to whatever it was circling. This is the equivalent of watching a runner come around the tightest bend of a track. You do not need to see the whole race to measure how fast they are moving, and that speed at the closest point tells you exactly how strong the gravitational field is at that distance. This is what Kepler worked out centuries ago. The relationship between orbital speed, orbital distance, and the mass of the central object is locked in by the physics of gravity. There is no ambiguity in the math. If you know how fast an object is moving at a given distance from whatever it is orbiting, and you know how that orbit is curving, you can calculate the mass of the unseen body. It does not matter that the unseen body is invisible. It does not matter that it emits nothing. The motion of the visible star is the measurement. The mass of the hidden companion is the answer. The team ran those calculations. The numbers they pulled from the arc of this star's path during its closest approach pointed to a companion with a mass somewhere above 3 solar masses. That lower bound alone was already significant. Neutron stars, the densest objects that are not black holes, rarely exceed 2 solar masses. The most extreme neutron stars theorized in physics might push toward 3, but a compact object sitting clearly above that threshold, with no visible light, no detected radio signal, and no X-ray emission, has only one reasonable identity. The invisible companion is not a neutron star. It is too heavy. What made the case especially solid was the quality of the closest approach data. That portion of the orbit, when the star is swinging fastest through its tightest arc, produces the strongest gravitational signal. It is the moment the companion's mass asserts itself most clearly in the star's motion across the sky. The team had 2 decades of Hubble measurements telling them exactly where the star was at each point along that arc. And they had James Webb infrared data sharpening the most recent position measurements to reduce uncertainty even further. The arc was clean. The curvature was real. The speed at closest approach was measured, not inferred. An ordinary star, unremarkable by every standard, curving through the dense interior of one of the most crowded places in the galaxy, not because of any visible neighbour, not because of the cluster's collective gravity pulling it off course, because something dark and massive and invisible had it on a leash 94 years long, and physics had been quietly recording the evidence for 2 decades in a telescope archive that nobody had looked at in quite this way before. The star's curved path, measured at the moment when it was moving fastest around its unseen partner, pointed to a dark companion massive enough that only one kind of object could explain it. The black hole now has a name. After more than 2 decades of archival data, careful measurement, the combined power of 2 space telescopes, the team formally designated their discovery oMEGACat BH2, the first confirmed stellar mass black hole ever found inside Omega Centauri. The name is not arbitrary. oMEGACat refers to the larger catalogue project built from that long, painstaking effort to map the precise motions of stars across the cluster. BH stands for black hole. The number 2 reflects this object's place within that catalogue framework, and that placement carries its own story. BH1 was not a previous black hole detection that got quietly overshadowed. BH1 was the same binary system, studied earlier by a different research team, that concluded at the time that the invisible companion was a neutron star. This new paper did not just find a black hole, it resolved an existing scientific dispute and reclassified an object that the field had already been arguing about. That is a different kind of discovery, and in some ways a more satisfying one. The person who led it was an undergraduate student, Matthew Whitaker, a research assistant at the University of Utah in Salt Lake City, is the lead author on the paper. Not a postdoctoral fellow, not a senior researcher with 30 years of telescope time behind them, an undergraduate. This detail tends to get buried in the press releases under layers of institutional language, but it is worth holding on to. The analysis required sifting through more than 2 decades of Hubble archival data, incorporating James Webb infrared observations, constructing a precise orbital solution for a star in one of the most crowded stellar environments in the Milky Way, producing a mass measurement tight enough to settle a debate between 2 research teams. That Whitaker led this work as an undergraduate says something about where serious astronomy can happen now, about what becomes possible when you have access to decades of archived observations from the most powerful space telescopes ever built. He was not working alone. Anil Seth of the University of Utah, a co-author and experienced researcher in stellar dynamics and compact objects, was part of the collaboration. So was Maximilian Habeler, a postdoctoral fellow at the European Southern Observatory, who led the data reduction for both the Hubble and Webb observations. Getting precise astrometric positions out of a field as dense as Omega Centauri is not a simple processing task. The stars are packed close enough that their light bleeds together in the detectors. Separating them cleanly, measuring the position of one specific star across observations taken years or decades apart, requires careful, methodical work. Habeler's role in that reduction was not a supporting act. Without accurate positions, there is no orbital solution. Without an orbital solution, there is no mass measurement and no black hole. The paper itself was published and announced formally, and the response from the astronomical community was not subdued. This is the kind of result that the field had been waiting on for a long time, not because researchers were impatient, but because the silence had been so complete for so long. Every previous method had returned nothing, or at least nothing definitive. The theoretical models kept insisting there should be thousands of black holes in there. One confirmed detection, with a well-measured mass and a clear orbital solution, changes the nature of that silence. It moves the question from whether black holes exist in Omega Centauri to how many there are and how quickly we can find them. The formal name itself carries an understated weight. oMEGACat BH2. 7 characters that represent decades of looking, 2 of the most capable telescopes humans have ever launched, an undergraduate's careful analysis. The resolution of a years-long dispute over what a single moving star in a crowded cluster was actually orbiting. Astronomy has a long tradition of compressing enormous effort into compact designations. This one follows that tradition faithfully. The object it refers to is 18,000 light-years away, roughly 4 solar masses, completely dark, invisible to every detection method anyone tried before this one. What makes the formal confirmation significant is not just the object itself, but what it represents in context. Omega Centauri should, according to every model of stellar evolution and cluster dynamics that researchers have developed over decades, contain something in the neighborhood of 10,000 stellar mass black holes. Those models are built on well-tested physics, the initial mass function of stars, the rate at which massive stars form and die, the dynamics of how black holes move and accumulate inside a dense gravitational environment. None of that is speculative. The prediction of 10,000 is not a guess. It is an estimate grounded in the same physics that correctly predicted the structure of neutron stars, the rate of stellar evolution, the frequency of supernova events in other environment, moments. And yet, before this result, not one of those predicted black holes had been directly confirmed through a measured mass. Now one has. The theoretical architecture suddenly has an observational anchor. There is something almost stark about that arithmetic. The cluster holds 10 million stars. It spans 150 light-years. It has been studied in one form or another for nearly 2,000 years, and the total count of confirmed stellar mass black holes inside it, as of this discovery, is 1. The gap between the prediction and the confirmed count is not a small rounding error. It is essentially the entire predicted population still hiding. This first detection is genuinely significant precisely because it confirms the method works. The astrometric approach that Whittaker's team applied is capable of finding these objects in this environment. That is not a minor technical footnote. That is the thing that makes the next detection possible, and the one after that. One down, and if the theoretical models are right, roughly 9,999 to go. The companion star takes 94 years to complete one full orbit around the black hole. That number is worth sitting with for a moment. Most black hole binary systems known to astronomers feature companion stars that complete their orbits in days, weeks, or at most a few years. Some take hours. The fastest orbiting binaries whip around their dark partners so quickly that the companion star is nearly grazing the black hole's gravitational edge. 94 years is not that. 94 years is slower than the orbital period of Neptune around our own Sun. It is the longest orbital period of any black hole binary system ever measured. When the research team realized what they were looking at, that number alone told them something significant about the physical arrangement hiding inside Omega Centauri. To understand what a 94-year period means, you need to think about what period actually tells you. Orbital period is tied directly to separation. The farther apart two objects are, the slower they move around each other and the longer each orbit takes. A planet close to its star completes an orbit quickly. A planet at the edge of a solar system takes centuries. The same logic applies here. A companion star with a 94-year period is not huddled close to its black hole. It is far away, circling at a distance that, by the standards of black hole binaries, is enormous. The two objects are gravitationally bound, but physically separated by a gulf that makes this system look almost casual in comparison to the tight, violent pairs astronomers usually detect. This wide separation is precisely why the system was invisible to conventional searches for so long. Most methods used to find black hole binaries depend on proximity. X-ray searches work when a companion star is close enough to the black hole that gas is actively being stripped from the star's outer layers, pulled across the gap, heated to tens of millions of degrees as it falls inward, and blasted out as high-energy radiation. At the distance implied by a 94-year orbit, that process barely happens. There is no significant mass transfer. There is no disk of glowing hot gas spiraling inward. The black hole is sitting there in the dark, pulling the star in a slow arc, and doing essentially nothing else that would betray its presence to a telescope looking for X-rays or radio signals. The system is quiet, not broken, not inactive, just quiet. What the team did have, after more than 20 years of Hubble observations, was the star's path through space. That path was curved, and curved paths require an explanation. In those 2 decades of data, the star completed less than a quarter of its full 94-year orbit, but the team captured the right quarter. The star was near its closest approach to the black hole during that observational window, which is the phase of the orbit where it moves fastest. Think of a comet swinging around the Sun. It accelerates as it approaches, reaches peak speed at closest approach, then slows again as it pulls away. The geometry of this observation window was fortunate in exactly that way. The star was at its most measurably fast. That speed, combined with the shape of the arc and an understanding of Kepler, its laws, was enough to calculate the mass of the invisible object anchoring the system. Here is what that mass and that separation and that 94-year period collectively describe. 2 objects in a wide, slow, gravitationally delicate embrace, separated by a distance far greater than anything seen in previously known black hole binary systems, orbiting each other so slowly that by the time the companion star completes 2 full orbits, The United States will have held roughly 47 presidential elections. The system is real, it is bound, but it is also fragile. Omega Centauri is not an empty neighborhood. It contains 10 million stars crammed into a volume roughly 150 light-years across. In that environment, close encounters between objects are not rare events on astronomical timescales. They are routine. An isolated pair of objects orbiting each other at wide separation in the middle of that density is like a loose handshake in a crowd. Eventually, something jostles it apart. The research team ran the numbers on how long oMEGACat BH2 can be expected to survive as a bound binary system in that environment. The answer was less than 1 billion years. That sounds long. Against a human lifespan, it is incomprehensible. Against the age of Omega Centauri, which is roughly 12 billion years old, it is brief. The cluster formed when the universe was young. This particular binary, by contrast, was almost certainly assembled recently through a chance dynamical encounter between an isolated black hole and a passing star, and it will be disassembled by a similar encounter long before the cluster finishes its own story. Ancient cluster, newly formed pair. A system that took more than 20 years of observations to detect is itself a temporary arrangement, one that will be broken apart by the chaos of the surrounding cluster long before the cluster itself grows old. Before this team's result, a different group of researchers had looked at the same binary system and come to a different conclusion. Their answer was a neutron star. Not a black hole. The distinction matters enormously, and it is worth pausing on why. Both objects are the collapsed remnants of massive stars that died in supernova explosions. Both are extraordinarily dense. Both are dark, but they are not the same thing. A neutron star is the crushed core of a dead star, packed so tightly that protons and electrons have merged into neutrons, held up against further collapse by the pressure those neutrons exert against each other. A black hole is what happens when that pressure fails. The core collapses past every known stopping point and disappears behind an event horizon. One is an extremely exotic object. The other is a point where the normal laws of physics as we understand them break down. Calling something a neutron star when it is actually a black hole is not a rounding error. It is a fundamentally different verdict about what that object is. The earlier team was not making a reckless claim. Their data supported it. What they had was a shorter window of observations, and with that shorter window, the mass of the invisible companion could only be constrained to a range. That range overlapped with the upper end of neutron star masses. The most massive neutron stars ever measured sits somewhere between 2 and 2.5 solar masses. Under some theoretical models, a neutron star could conceivably reach 3 solar masses before collapsing further, though no confirmed example of one that heavy has ever been found. If the measurement uncertainty on the companion's mass was wide enough to include that territory, calling it a neutron star candidate was a scientifically defensible position. It was cautious. It was appropriate given the data available. It just turned out to be wrong. What Whittaker's team did was straightforward in principle and extraordinarily demanding in practice. They went back to the archive. Hubble has been observing Omega Centauri for decades, and the earlier study had not used all of it. Whittaker's team pulled astrometric data stretching from 2002 all the way through 2023. That is more than 20 years of positional measurements for the same star, tracing the same slow arc around the same invisible object. Where the previous group had worked with a shorter slice of that orbit, this team had a much longer one. More of the arc, more of the curve, more leverage, mathematically, to pin down the mass at the other end of the gravitational leash. Then they added something the earlier study could not have had. The James Webb Space Telescope, operational only since 2022, had observed Omega Centauri and captured the companion star in the near-infrared. That matters because Omega Centauri is one of the most crowded environments in the galaxy. When you are trying to measure the precise position of a single star buried inside 10 million others, your ability to separate it from its neighbors is everything. Webb's infrared sensitivity and sharper angular resolution cut through that crowding more cleanly than Hubble could alone. The most recent position measurements, the ones anchoring the far end of the 20-year baseline, came out sharper. The orbital arc snapped into focus. With a tighter arc comes a tighter mass estimate. The uncertainty shrank. The range that had once extended down into neutron star territory no longer reached there. The lower bound of the companion's mass rose above the theoretical ceiling for neutron stars. The companion weighed in at 4.46 solar masses. That is not a borderline case. That is not a number that sits ambiguously between two possible explanations. No neutron star has ever been confirmed at that mass. The physics of neutron star structure puts a hard ceiling somewhere between 2 and 3 solar masses, and the most generous theoretical extensions to that ceiling still fall well short of 4.46. An object that heavy, dark, and compact has only one identity available to it. This is where the longer baseline earns its value. 20 years of Hubble data is not just more data. It is more data gathered during the portion of the orbit when the companion star was swinging closest to the black hole, accelerating through its fastest motion. The faster a star moves around an unseen companion, the more precisely you can infer that companion's gravitational pull, and the more precisely you can calculate its mass. The previous team had observed part of that arc. Whittaker's team observed more of it, anchored the measurements more precisely with Webb, and ran the same physical equations with much tighter inputs. The answer shifted decisively. The earlier researchers were not wrong to be cautious. With the data they had, caution was exactly the right scientific instinct. What they could not do was collect observations that had not yet been taken. At 4.46 solar masses, the invisible companion is too heavy to be anything other than a black hole, and the addition of 2 more decades of Hubble data and James Webb's sharper infrared eye made the case definitive. Here is the part of the discovery that does not fit the textbook. Once the team had confirmed that the invisible companion in this binary was a black hole, they had a mass to work with, 4.46 solar masses. That number should have been exciting for one reason and quietly troubling for another. It was exciting because it confirmed a black hole. It was troubling because the number was lower than anyone expected to find in Omega Centauri, not slightly lower, noticeably puzzlingly lower. And the reason that matters requires understanding something about the chemistry of ancient stars and what that chemistry does to a massive star's fate. Astronomers use the word metallicity to describe how many heavy elements a star contains. In this context, heavy means anything heavier than hydrogen and helium. Carbon, oxygen, iron, silicon, everything that gets forged inside stars and scattered through space when those stars die. Young stars forming in regions already enriched by earlier generations of stellar deaths tend to be metal-rich. Old stars, born when the universe was still young and mostly hydrogen and helium, tend to be metal-poor. Omega Centauri is one of the most metal-poor environments in our immediate cosmic neighborhood. Its stars are ancient, formed early, built largely from the 2 lightest elements in the periodic table. This matters because metallicity drives something called stellar wind. When a massive star is alive, burning through its fuel, radiating enormous amounts of energy, the pressure of that radiation pushes material off the star's outer layers in a continuous stream. The strength of that wind depends heavily on how many heavy elements are present. Metal-rich massive stars have strong winds. Over their lifetimes, they shed a substantial fraction of their total mass this way, blowing it out into the surrounding space before they ever get to collapse. When the collapse finally comes, the core that remains is lighter than it would have been if the star had held on to all that mass. Lighter core, lighter black hole. Metal-poor massive stars behave differently. Fewer heavy elements means a weaker wind. A weaker wind means less mass lost during the star's lifetime. The star arrives at the moment of collapse heavier than a comparable star born in a metal-rich environment would. Heavier core. heavier black hole. The physics is direct, the prediction follows naturally from it. In a metal-poor cluster like Omega Centauri, you would expect stellar mass black holes to sit toward the upper end of the stellar mass range, not the lower end. The models were consistent on this point. Researchers working on globular cluster dynamics had built it into their population estimates for decades. Then the first measured stellar mass black hole in Omega Centauri came in at 4.46 solar masses. That is not a featherweight. It is still definitively a black hole, still more massive than any known neutron star. But in the context of what a metal-poor environment was supposed to produce, it is unexpectedly light. Something in that picture is not adding up. The question is what? Several possibilities are sitting on the table, none of them settled. One is that the stellar wind models for metal-poor massive stars are incomplete. The standard picture may be missing additional mass loss mechanisms that operate even in low metallicity environments, instabilities in the star's outer layers, pulsation-driven ejections, other processes that are not well constrained by current models. Stars this massive and this old are difficult to study directly. Most of the stars that would have produced the black holes now sitting inside Omega Centauri lived and died billions of years ago. The models of their lives are built from theory and indirect evidence, not from direct observation of the stars themselves. A second possibility is that the black hole's mass was shaped after formation. Inside a cluster as dense as Omega Centauri, black holes do not simply sit quietly once they are born. They move through a field packed with other stars and objects, and they interact. In some of those interactions, energy is exchanged. In some, objects are ejected. It is at least conceivable that the object now known as oMEGACat BH2 was originally more massive and shed some of that mass through encounters, a dynamical history that left it lighter than it started. This is speculative, and verifying it would require understanding the object's entire life inside the cluster, which is not something any current instrument can reconstruct in detail. A third possibility, harder to dismiss than it sounds, is that this black hole formed through a different pathway entirely. Not the straightforward collapse of a single massive star, but something more complicated. A merger, a partial collapse, an event that produced a black hole through a route the standard stellar evolution models do not account for in the same way. Omega Centauri's extraordinary density makes unusual formation pathways more likely there than almost anywhere else in the Milky Way. None of these explanations has been ruled out. None has been confirmed. The mass of oMEGACat BH2 is not what the models said it should be, and nobody has a clean explanation for why, which means the discovery has both answered one question and opened another. The star and the black hole did not form together. They were strangers in the most literal astronomical sense. Two objects born at different times from different gas clouds in different parts of a cluster that has been churning through stellar births and deaths for over 12 billion years. At some point their paths crossed. The geometry was right. They never separated. Understanding how that happens requires understanding what Omega Centauri actually looks like from the inside. 10 million stars packed into a volume roughly 150 light-years across. That number is easy to say and almost impossible to picture. Our own solar neighborhood contains maybe a handful of stars within 10 light-years of the Sun. Omega Centauri contains thousands within the same radius. Near its core, many more than that. The average distance between stars in its densest regions is a small fraction of the distance between our Sun and its nearest neighbour. Objects in there are not isolated. They are constantly passing near each other, tugging at each other, exchanging energy, altering trajectories over timescales that feel short by the standards of a 12-billion-year-old cluster. This is not a calm environment. It is a gravitational crowd. When a massive star inside Omega Centauri exhausted its fuel and collapsed into a black hole, that black hole did not disappear. It stayed in the cluster. Gravity held it there, but it did not necessarily stay near whatever companion it might have had at birth. black holes are more massive than most of the stars around them, and over time, through repeated gravitational interactions with neighbours, massive objects in dense clusters tend to sink toward the centre. This is called mass segregation, and it means the black holes in Omega Centauri have been slowly concentrating themselves for billions of years. A black hole drifting through that environment is not drifting through empty space. It is moving through a field of potential encounters. Here is what happens when a black hole and a star pass near each other at the right speed and the right angle. The black hole's gravity pulls on the star, bending its path. If the encounter were perfectly isolated, the star would curve around the black hole and continue on its way. A hyperbolic trajectory, no binding, no orbit. But in a dense cluster, nothing is perfectly isolated. There are other stars nearby. As the black hole and the passing star interact, energy can be transferred to or from those surrounding objects. The right conditions bleed enough energy out of the encounter that the star and the black hole, instead of flying apart, end up gravitationally bound, not locked into a tight, close orbit, something looser, a wide, elongated path that the two objects settle into over subsequent interactions with the surrounding field. Astronomers call this kind of process a dynamical capture, or sometimes an exchange interaction, particularly when a black hole replaces one member of an existing binary pair. The 94-year orbital period of oMEGACat BH2's companion star fits this picture cleanly. Objects that form together from the same collapsing gas cloud tend to end up in relatively compact orbits. The cloud itself has limited size, and the resulting objects begin their lives close to each other. Objects that found each other later, through gravitational encounters in a dense field, tend to settle into much wider orbits because the capture process is inefficient, and the energy exchange that binds them leaves them at large separations. A 94-year orbit implies a physical separation between the star and the black hole that is vastly larger than what you would expect from a primordial binary. That wide spacing is a signature, not a random property. It tells you something about how these two objects came to be paired. There is a consequence to that wide orbit, and it cuts in an uncomfortable direction. The same cluster density that enabled the capture will eventually destroy it. Other stars passing close to the binary will perturb it, stealing energy from the system or injecting energy into it. Over enough time and enough encounters, the perturbations accumulate. The binary widens further, the gravitational binding weakens, and eventually a passing star delivers enough of a gravitational push that the companion breaks free. The team calculated that a system with these properties will survive for less than 1 billion years before being disrupted. The cluster is 12 billion years old. The binary is, by that measure, newly assembled. This is one of the stranger things the discovery reveals. The binary system detected by Hubble and Webb is not an ancient relic of Omega Centauri's early history. It was built recently inside a cluster that has existed since nearly the beginning of the universe. Black holes and stars inside this cluster are still pairing up, still forming new systems, still writing the current chapter of a story that began more than 12 billion years ago. The density of Omega Centauri, the same property that makes it so hard to search, also makes it one of the most active places in the galaxy for black holes and stars to stumble into each other's gravity and never fully escape. Omega Centauri still has an effectful logical energy. Sitting at the cluster's core, something far more massive has been quietly building a case for its own existence. It has not been formally confirmed, but the evidence has been accumulating for years. With each new study, the alternative explanations have gotten harder to defend. This second object belongs to a completely different category. Stellar mass black holes like oMEGACat BH2 top out somewhere in the range of a few dozen solar masses under normal circumstances. Supermassive black holes, the ones anchoring the centers of galaxies, run into the millions and billions. Between those two extremes sits a class that astronomers have spent decades trying to pin down: intermediate mass black holes, typically defined as objects with masses somewhere between a few hundred and a few 100,000 suns. They are theoretically important, genuinely difficult to confirm, and frustratingly rare as definitive detections go. The suspected object at the center of Omega Centauri is one of the most studied candidates in this entire category. The evidence comes from stellar velocities. Stars near the center of Omega Centauri are moving faster than they should be. This is not a subtle effect buried in noisy data. It is a measurable, repeatable signal that has shown up across multiple independent studies using Hubble observations. When you map out how fast stars are orbiting near the core, and compare that to how much visible mass is present in that same region, the numbers don't balance. The stars are moving as if something invisible and enormously heavy is sitting at the center, pulling on everything nearby. The excess is substantial. Models that try to explain the velocity distribution without a central massive object require increasingly uncomfortable assumptions about how the cluster's stars are arranged. A central intermediate mass black hole fits the data more naturally. The mass estimates for this suspected object have varied between studies. That is part of why confirmation remains elusive. Some analyses have put the mass at around 8,000 solar masses. Others have suggested it could be higher. The range reflects the genuine difficulty of the measurement. Omega Centauri's core is extraordinarily crowded. Separating the gravitational influence of a central massive object from the combined pull of thousands of densely packed stars requires precision that pushes the limits of current instruments. Each new dataset has tightened the constraints, but the uncertainty has not collapsed to zero. This is not the kind of situation where one dramatic observation settles the question overnight. What makes the intermediate mass black hole hypothesis compelling is that it also fits what astronomers expect from Omega Centauri's probable origin. If the cluster is genuinely the stripped core of a former dwarf galaxy, then its central object is not merely a feature of cluster dynamics, it is the remnant of a galactic nucleus. Dwarf galaxies are known to host black holes at their centers, scaled-down versions of the supermassive objects that anchor larger galaxies. If Omega Centauri's progenitor galaxy had a central black hole, if that nucleus survived the stripping process intact, then the dense core we observe today would naturally contain it. The intermediate mass black hole would be, in this reading, the gravitational fingerprint of an entire galaxy that no longer exists in any other form. This is where the two discoveries start to interact in a way that is theoretically significant. oMEGACat BH2 sits somewhere in the broader cluster, far from the core, a stellar mass black hole caught in a wide binary with a normal star through dynamical capture. The suspected intermediate mass object sits at the center, far more massive, anchoring the gravitational structure of the whole system. These are not the same kind of object, formed the same way, detected the same way, or occupying the same region. They are different classes of black hole, potentially coexisting within the same cluster at the same time. No other environment in the galaxy has offered astronomers this particular combination. The theoretical implications of that combination are considerable. Mass segregation, the process by which heavier objects sink toward the center over time, means that many of the cluster's stellar mass black holes are predicted to congregate near the core. If a genuine intermediate mass black hole is sitting there, those stellar mass objects would be orbiting it, interacting with it, occasionally being ejected by close encounters with it. The central massive object shapes the distribution of the surrounding population. Understanding one without understanding the other gives you an incomplete picture of what is actually happening inside Omega Centauri. The case for the central object has not yet crossed the threshold that most astronomers would call definitive. The velocity measurements are compelling, the models fit, and the origin hypothesis supports it, but definitively ruling out alternative explanations, dense concentrations of neutron stars, stellar remnants of other kinds requires data that current instruments can only partially deliver. Upcoming observations, better angular resolution, longer baselines will sharpen the picture. If both the central massive object and the surrounding population of stellar mass black holes are eventually confirmed in detail, Omega Centauri would become the only place in the galaxy where astronomers can study multiple classes of black holes interacting in real time within the same environment. The discovery of oMEGACat BH2 matters far outside the immediate question of black holes in Omega Centauri. Since September of 2015, a detector called LIGO has been picking up ripples in the fabric of space-time itself. These ripples are gravitational waves, and the ones LIGO detects most often come from black holes colliding. Two black holes, each several times the mass of our Sun, spiraling toward each other over millions of years, finally merging in a fraction of a second and releasing more energy than all the stars in the observable universe emit in that same instant. LIGO has now catalogued dozens of these events. The signals are real, the physics is confirmed, and the detections keep coming. What is not settled is where those merging pairs are coming from in the first place. This is the kind of problem that keeps theorists arguing late into the night. There are two leading candidates for where merging black hole pairs originate. The first is isolated binary star systems, two massive stars that formed together, lived together, died together, left behind two black holes already gravitationally bound from birth, tightening their orbit over billions of years until they finally collide. The second candidate is exactly the kind of environment we have been talking about for the last several paragraphs: dense stellar clusters, where black holes that formed independently find each other through dynamical encounters and pair up in the chaos of a crowded gravitational field. Both pathways are plausible, both are probably contributing. The question is how much, and in war, to proportion. The answer depends entirely on how many black holes are actually inside dense clusters like Omega Centauri, how efficiently they pair up once they are there. Here is why the numbers matter. If globular clusters like Omega Centauri are genuinely full of stellar mass black holes, as the models predict, if those black holes are regularly pairing up through dynamical interactions, then a substantial fraction of the gravitational wave events LIGO detects could be tracing back to environments exactly like this one. Every merger signal LIGO records is a message that travelled across the universe, but it carries almost no return address. You can measure the masses of the two objects that merged. You can measure the distance roughly. What you cannot easily determine from the wave signal alone is what kind of environment those objects lived in before they found each other. To answer that question, you need independent constraints. You need to know, from direct observation, how many black hole binaries actually exist inside globular clusters, what their masses are, how wide their orbits are. oMEGACat BH2 is one of the first direct data points the field has ever had. A real black hole, measured at 4.46 solar masses in a real binary system, inside a real globular cluster, with a real orbital period of 94 years. That is not a theoretical prediction. That is a measured object with measured parameters. Theorists building models of black hole populations in globular clusters, connecting those populations to gravitational wave event rates, now have something concrete to test their models against. Before this, those models were being calibrated mostly against theoretical expectations and indirect constraints. The gap between prediction and direct measurement was vast. It is now slightly less vast. The 94-year orbital period of oMEGACat BH2 also tells you something specific about how dynamically formed binaries behave. This system is wide. The black hole and its companion star are separated by a large distance by the standards of known binary systems. That wide separation is itself a signature of dynamical formation rather than coevolution from a shared birth cloud. Wide binaries do not merge quickly. They need to be hardened over time through additional interactions with surrounding stars. Each close encounter stealing a little energy from the orbit and drawing the two objects slightly closer together. That process takes time. In a cluster as dense as Omega Centauri, interactions happen more frequently than almost anywhere else in the galaxy. The cluster's own extraordinary density. Why is what makes it such an efficient factory for producing the kind of pairs that eventually end up in LIGO's detectors. Anil Seth of the University of Utah One of the collaborators on this discovery stated the connection plainly. Dense stellar environments like Omega Centauri are primary places where black hole binaries are expected to form and eventually merge. Understanding the process of forming black holes and then dynamically forming binaries, he noted, is essential for interpreting gravitational wave events. That is not a tangential observation. That is the central scientific motivation connecting a star cluster 17,700 light-years away to detectors buried underground on Earth, waiting for the universe to shudder. There are roughly 150 known globular clusters in the Milky Way alone. Across all the galaxies we can observe, the number runs into the hundreds of thousands. If even a fraction of them hold populations of stellar mass black holes approaching what Omega Centauri's models predict, the total contribution of dense cluster environments to the gravitational wave event rate could be enormous. Every real black hole binary found and measured inside a real globular cluster gives theorists one more anchor point for understanding where the gravitational waves LIGO keeps detecting are actually coming from. One black hole found, 9,999 by the model's accounting, still sitting in the dark inside Omega Centauri, invisible, undetected, almost certainly still there. That gap between 1 and 10,000 is not a failure, it is a starting line. And the question now is not whether the rest of them exist, but whether astronomers have the tools and the time to find them. The same astrometric technique that uncovered oMEGACat BH2 is the obvious next step. The Hubble archive for Omega Centauri does not end with the observations that went into this discovery. Decades of data covering tens of thousands of individual stars are sitting in that archive, most of it never analysed for the specific signature of a star tracing a curved path around something invisible. Each star in the cluster that has been observed across multiple epochs is, in principle, a candidate. Not every one of them will be orbiting a black hole. The vast majority will be moving in perfectly ordinary straight lines, following the general drift of the cluster through space. But somewhere in that population, if the theoretical prediction holds, are more stars behaving the way oMEGACat BH2's co-Manpanian behaved, curving, accelerating, tracing an arc that the cluster's own motion cannot explain. Applying this systematically is not a trivial problem. The crowding inside Omega Centauri is the same obstacle it has always been, separating individual stellar positions from the blur of 10 million neighbours at a distance of nearly 18,000 light-years. Requires the kind of precision that pushes Hubble to the edge of what it was designed to do. It requires measuring positions to a fraction of a pixel, doing that consistently across observations taken years or even decades apart. The fact that it worked once, for one system, is proof that the technique is sound. Scaling it up to cover the full cluster is a different kind of challenge. Slower, more methodical, more dependent on computational work than on telescope time. This is exactly the kind of problem that the Nancy Grace Roman Space Telescope was built for. Roman is not yet launched, but when it begins operating, it will do something that neither Hubble nor Webb was designed to do at this scale. It will image large sections of the sky repeatedly with Hubble quality resolution and a field of view roughly 100 times wider. For astrometric searches, that combination is transformative. Instead of pointing at a specific cluster and building up observations slowly over years, Roman will sweep through the galactic bulge on a regular cadence, collecting precise positional data on enormous numbers of stars during every observing run. The same star, measured again and again across months and years, will eventually reveal whether its path is straight or curved. A system with the orbital period of oMEGACat BH2 takes roughly 94 years to complete one loop. Roman does not need to observe the full orbit. It needs to observe enough of it at the right moment to detect the curvature. The regular cadence means that moment is far less likely to be missed. Omega Centauri is not the only target. The Milky Way contains well over 100 globular clusters. Many of them have been stared at by Hubble for decades. Most of that archival data has never been examined for astrometric black hole signatures. The technique validated in Omega Centauri works on the same physical principles regardless of which cluster you apply it to. Any dense stellar environment old enough to have produced and retained a population of stellar mass black holes is a candidate for this kind of search. The archive is already there. The method is proven. What is needed is the systematic effort to work through it. That effort will have limits. Some of the predicted 10,000 black holes inside Omega Centauri are almost certainly isolated. No stellar companion, no orbital motion to track, nothing to give them away through astrometry or any other method currently available. A dark object, sitting alone in a dense stellar field, not accreting, not orbiting anything bright enough to measure, is effectively invisible to every instrument we have. Astrometry depends entirely on having a visible companion star, whose motion reveals the hidden mass. Black holes without companions remain beyond reach for now. How many of the 10,000 fall into that category is not known. The models can estimate it, but the true fraction will not be clear until the search has gone further. Still, even a partial census would be significant. Every black hole binary confirmed inside Omega Centauri adds a real data point to the population models, tightens the constraints on stellar evolution in metal-poor environments, sharpens the predictions for gravitational wave event rates. The search does not need to find all 10,000 to matter. It needs to find enough to test whether the prediction was correct in its broad outline, to reveal whether the population has properties, masses, orbital configurations, formation histories that match what the models say they should. The technique works. The archive is full. The search that has barely started is almost certainly going to get a great deal more interesting before it is done. The deeper lesson from oMEGACat BH2 is not really about one black hole in one star cluster. It is about a pattern that astronomy keeps repeating, quietly, every few decades, when a new method arrives and suddenly reveals a population of objects that the previous generation of instruments was completely blind to. The black holes were not hiding because they are rare. They were hiding because nobody was looking in the right way. That distinction matters enormously. There are roughly 150 known globular clusters in the Milky Way. Most of them have been observed by Hubble across decades. Many of those archival datasets have never been searched using astrometry. Nobody has systematically gone through them looking for companion stars tracing curved paths around invisible massive objects. That work has barely started. If even a fraction of those clusters hold black hole populations proportional to what Omega Centauri's models predict, the number of stellar mass black holes sitting undetected in our own galaxy's globular clusters alone is enormous. Add every other galaxy in the observable universe, each with its own population of globular clusters, and the implied total becomes genuinely difficult to hold in your mind. The computational demands of such a systematic search would be substantial. Astrometry on archival images requires matching stellar positions across decades-long baselines, accounting for proper motion, parallax, and the systematic errors that accumulate when processing millions of individual observations. Modern machine learning algorithms have made this feasible, but the work remains labor-intensive. Universities and observatories would need to commit significant resources to this project. The payoff, however, is a complete census of stellar mass black holes in our local universe, rather than the fragmentary picture we have now. This represents the magnitude of discovery that rouses astronomers from complacency and back to their data archives. Not the single detection, but what it implies about everything that is still out there. oMEGACat BH2 is not just a discovery, it is a proof of concept. The technique works, the archive exists. The question now is whether the field has the patience and the computing resources to apply it systematically, cluster by cluster, star by star, curved path by curved path. Omega Centauri itself is 17,700 light-years away. At that distance, measuring the position of a single star to a fraction of a pixel over 2 decades, in the middle of a field containing 10 million other stars, was considered nearly impossible until recently. The fact that it worked, that one curved trajectory emerged cleanly from all of that crowded noise suggests the method is more powerful than even its proponents initially claimed. What works at 17,700 light-years in one of the densest stellar environments in the galaxy will work elsewhere. And the universe is full of elsewhere. Every globular cluster that formed around a galaxy like ours went through the same process. Massive stars were born, lived fast, and died, leaving black holes behind. Those black holes did not evaporate. Gravity does not give refunds. They are still in there, sitting in the dark, revealing themselves only to the motion of whatever happens to be orbiting them. Most have no companion. Most will never be found. But the ones that do have companions, the ones tracing those slow curved paths through the crowded field, are waiting for someone to look carefully enough and long enough to notice. The sky above Omega Centauri holds, somewhere in that dense bright smear of ancient light, 9,999 more objects waiting for the same patience, the same precision, and the same willingness to look for things that refuse to announce themselves.